Hi Chris, this is your feedback video for the Circular Motion 2 homework. Let's start with question 1. Okay, so they ask you to draw the forces acting on the car in both diagrams. So I can see you've labelled the reaction force here. It's the same size as the weight, which is correct. Here you've labelled it perpendicular to the surface, which is good. However, friction. Sorry Chris, I had to pause there for a second. Okay, yeah, so the friction force, unfortunately these aren't right. You've got friction pointing to the left. For a start, it's a force diagram, so the force arrow has to start on the object. In this diagram, the friction acts that way. Friction will try and oppose the car from sliding outward. Okay, think about if there was no friction, if this was a frictionless road. Car may be going round a bend and the center of the circle is over here, okay, or round a roundabout and the center of the roundabout's over here. The car would tend to slide outward away from the center of the roundabout if there was no friction. Friction is opposing that. Friction is a force in that direction. So the friction arrow should look like this in this diagram, and it actually acts parallel to the slope in this diagram, like this. Okay, because it's going to oppose the car from sliding up the slope. So unfortunately, because they are wrong, I can't give you any marks here, okay, because you have to deduct marks for incorrect forces. Now, but this is good. What are the origins of the centripetal force? Could be provided by the horizontal components of the reaction force, yes, but it's not the weight. It's the friction force. So you got the reaction force. Let me just draw a vertical line. Let's call this theta. This reaction force has a horizontal component toward the center of the circle. That's partly what provides the centripetal force. But also this friction force here, that's theta there. This friction force has a horizontal component. So it's the horizontal components of the reaction force and friction force combined that provides the centripetal force. All right. This question here. Right, now, this answer here, it's not quite right. Let's have a look. All right, Chris, so the key thing you need to understand, it's talking about when the bike's in position Q, and it says the minimum speed which will keep the motorcycle in contact with the track. When the wheels are just in contact with the track, the reaction force will be 0. All right. So R is 0, so basically that's 0, that's 0. So it's just mg equals mv squared over r. Okay, the m's are going to cancel and you can find what v is. Okay, I'm going to add the marks up at the end. Okay, question 2, this looks good. Good. Yeah, good. Now this here is not right. What's the tension in the string? Okay, so you've just worked out that the centripetal force is this. Okay, now let's look at the diagram. So it's talking about when the bob is here at the bottom. Let's think about the forces acting on the bob. You've got the weight of the bob and you've got the tension in the string. The centripetal force is the resultant force toward the center of the circle. Okay, in other words, toward P. And that is T minus mg. T minus mg is the resultant force toward the center. So T minus mg equals mv squared over r, which is 2.9. So T minus mg equals let's use the unrounded number, 2.94. Now you can find T. Okay, so go ahead and redo this bit. Question 4, the van going over the humpback bridge. Draw the force diagram. Yeah, this is fine. You've got them the same length, roughly the same length. Just make sure that they are that both these forces are along exactly the same line. They are a little bit offset from each other, okay, but I'll give you the mark. This looks fine. Just let me double check. So you m bracket g minus v squared over r. Yeah, that's good. Good. Right. This bit here, what happens if the van goes over the bridge at a higher velocity? What happens to the reaction force of the van on the package? When V increases, R would decrease proportionally. I'm not sure what you mean by proportionally. I don't think that's kind of relevant really, but you just need to say it decreases. Yeah, so that's fine, just say it decreases. Now, you said here as V becomes 15 meters per second, R would head toward becoming 0. Good. You need to say what the significance of that is. When the reaction force is 0, what actually happens to the package? And what's going to happen is the package will lose contact with the floor of the van. Okay, so you need to write that down. Okay, let's look at the last question. This looks good. Good. Yeah, that was Mr. Cooper, I apologise. He just can't help himself. This answer's right, but you've only written it to 1 SF. So I can only give you 1 mark really for that. You need to write it, 2.0. Because if you look at all the data you've used to calculate this answer, everything is to 2 significant figures, isn't it? All the data at the top, tension given to 2 SF, so that needs to be 2.0. And then finally, this question here, let me just have a read through your answer. Okay, Chris, so I've had a read through it. Straight away, there's a bit of a kind of humdinger here. You said that it moves in a vertical circle. It's not, it's moving in a horizontal circle. I think it says it over here. Yeah, horizontal circle. Okay, I think that's just a careless error though, because I think the rest of it makes more sense. Okay, so you've said, okay, its velocity is changing because it's changing direction. That's good. You've said that means it's accelerating. Newton's first law says an object will be at rest or moving at a constant speed in a straight line if no resultant force acts on it. This confirms the existence of the centripetal force and that it acts opposing the other forces present. I'm not sure what that means. The centripetal force is provided by the tension. Yeah, specifically it's provided by the horizontal component of the tension. You see, we'll talk about this in the lesson. Reaction force occurs at the center of the circle, acting outwards to create an opposed equal reaction. This needs clarifying. It's not really, you haven't explained properly how the third law applies in this scenario. And this bit here about why the string can't be horizontal. The reason it can't be horizontal is because there has to be a force to balance the weight of the ball, and that force must be provided by the vertical component of the tension in the string. So the string has to be at an angle like this. Here's the ball, here's the weight of the ball, mg. What is there to oppose this force here to keep the thing in vertical equilibrium? Well, there's the tension. That tension force has, I haven't drawn this very, the tension force must have some vertical component. Let me draw the string like this. It has to have a vertical component, which, if the string was horizontal, the tension would not have a vertical component. So it has to have some kind of angle like this, so it has a vertical component to balance the weight. That's why the string can't be horizontal, why it will never be horizontal. But we'll talk more about this in the lesson. Okay, so quite a long video, Chris. I might have waffled a bit there, I apologise. So you've got a few things you need to work on here. All right, and if you have any other questions, then just let me know.